Okay, let's talk about IR, or infrared spectroscopy. Up until now, we have been talking about electronic transitions, which actually changes the energy between two different electronic states. That kind of delta E and frequency falls into the UV-Vis range. These kinds of transitions can be used for quantitative analysis in Beer's law because the number of photons that are absorbed are in fact proportional to the number of molecules that you have. Now we want to talk about these quantum transitions, which are not between electronic states, they are between the vibrational states within a single bond. This delta E is considerably smaller, somewhere in the vicinity of about 1/10 of the energy of the UV-Vis, and is associated with the vibrational bond frequency. That delta E is considerably smaller than the energy change for an electronic transition, and so the wavelength is much, much longer. The delta E, let's say typical for a CO bond, if it's about 1/10, would fall into the 10 to the minus 20th joules, and so typically for a CO, somewhere in the vicinity of about 2.3 times 10 to the minus 20th joules. If we have that energy, then we can calculate what its bond vibrational frequency is. 2.3 times 10 to the minus 20th joules equals H, which is still 6.6 times 10 to the minus 34th joules dot seconds. And that means if we solve for the frequency, we get 3.5 times 10 to the 13th cycles per second. So that means it's making 3 times 10 to the 13th vibrations in every second. That comes from the quantum definition, but really is associated with how many vibrations can occur in that CO single bond stretch. From that, we can also calculate the wavelength of light that is associated with that quantum transition. Again, we just use C is equal to lambda nu, and now that we know the frequency, we can calculate lambda. From that, we get a wavelength of about 86,000 nanometers. 8,600 nanometers, or 8.5 times 10 to the minus third centimeters. The wavelength is so long that you can actually talk about the wavelength of light that is absorbed by that bond in terms of centimeters. Organic chemists don't like using wavelength as a measure of their absorption frequency, so they created their own frequency proportional unit, which is, of course, inversely proportional to wavelength. So they just did reciprocal wavelength. So if we do 1 divided by 8.5 times 10 to the minus 3 centimeters, we get 1,200 reciprocal centimeters. That bond vibration of a carbon and an oxygen has a frequency proportional term that is called 1,200 reciprocal centimeters. That represents the speed at which it is vibrating.